They're awful. BurgerFi.
I'm
BurgerFi
a Five
had
Guys
the
over
absolute
Five
freaking
Guys.
best
I don't know that.
onion
is.
rings.
Five
It's
Guys.
over. It's off Windward. It's over near Ethan's house.
Oh,
So good.
Hey, mac and cheese is better than burgers.
I was 41.
No.
Mm.
Okay,
No.
if you're making
Sausage, egg, and cheese is better than.
See, I have a thing. If it's a fried egg, you eat it with bacon and toast. If it's a scrambled egg, you eat it with sausage and biscuit. It's not the same thing. I don't know why. It just
I would,
is.
I would rather 1,000,000% rather have a good good burger over a good
My family always like-
Mm.
No.
It-
If it was a good
I like a
sausage,
good
egg, and cheese over a good burger, I'd do sausage. egg. Sausage, egg, and cheese is my favorite.
Does anyone here like hot dogs more than burgers?
No.
Sometimes. 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 I said sometimes, not all the time.
Oh, do you put ketchup on your hot dog?
I try to avoid hot dogs.
Yeah, I've kind of started doing that.
I'm not.
Well, if I'm having
What's
a
the
hot
matter?
dog, only mustard.
I do ketchup.
You want me to get you fork?
Why do you like ketchup on a hot dog?
You're fine.
It's gross. It's gross. It's just too sweet for me.
I never got into relish.
Yeah.
I never really.
That's terrible. That's like when you get it at the drive-through and they don't give you something.
my gosh, thank you.
Like-
Jack wasn't looking at you.
I've gone through the drive-through and have them not give me a straw or
He wanted
something.
to see something.
What?
Mom.
What?
Nothing.
Okay, yes,
2 girls over there forgot their forks.
sure, honey. Thank you. I'm guessing they're your girls.
One more. One more.
There we go.
No, they were just too scared to interrupt.
Oh, that's sweet.
I'm the only one.
All right, so I do have it up on the screen today, but I don't think there's, I mean, if there's something super important, we'll just spin around.
Finger eater for mac and cheese.
I was thinking we might be using the
What?
screen, so.
When you forget the fork for mac and cheese.
Okay, that's disgusting.
No,
Who does that?
It's like a raspberry. You have to like slide the pasta onto your fingers.
Ew.
All right, I have a couple things to give back. Let me real quick. Michael, this is you.
I'm sorry, I'm just smashing my
Abby, this is you. Sorry, Alex, that's you. Jack. Hey. All right, so
Long mac and cheese.
let's do science now that we've talked about food without utensils. So
Oh, I put
I'll
mine in online. Okay.
and yeah,
I was like, where's mine? Oh.
yeah. A lot of people, yeah, this week was kind of wacky with stuff. All right, so acids and bases and solutions. So we just did a lab, which I hope y'all thought was fun. At least I thought it was fun.
Oh, cool.
We
Um,
had to deal with Alex distraction.
Alec and Drew, yes, you're
What
fine.
did her mom write?
So if we're going,
Drew, you risked our lives for science and you also risked you also were risked for because Alex was talking.
okay, you guys,
We did tricks.
guys.
That's actually nice.
So we're working on outlines, right? We're working on taking our notes from the book and putting it into an outline format so that it's easy to study and work with, right? So our unit here, or our Roman, no, not a unit, our chapter, whatever, our Roman numeral will be this acids and bases and solutions. That's the section of your chapter, I suppose. So this would be like your Roman numeral 1. And then we move on to A, which is the first little subsection, which is acids. So it's acids in acid solutions conduct what?
Electricity.
Right, and why? Why is that? What do they have floating around in them? Yeah, what kind of ion specifically? What's in the acids that's floating around?
I was about to say that.
Yes, okay. So when you put an acid in water, it's going to dissociate, and it'll dissociate into hydrogen, and then the conjugate base pair that's going to go with the base. What happens when you put an acid and a base together? What do they always make? There's always two products. Always.
Salt and water.
Salt and a water. All kinds of different salts, but salts and water. So that one of those hydrogens is going to pop off that acid, and water this itself will do this. Water will dissociate all on its own. So when you have the H that separates to one side and the OH to the other, you've got the hydrogen, the positively charged hydrogen, and it's a proton donor, and that's what's going to denote your acid. So obviously it's going to conduct electricity well because electricity deals with electrons, right? And they're negative, so here's your positive to your negative, so it makes perfect sense. And then your bases, and then your bases are going to have that hydroxide, which is the other part of the water molecule, the OH. So acids react with what? Metals, yeah, that's one way to tell that it's an acid, right? And then they generate, there we are, with hydronium. Okay, so hydronium itself is going to come from the hydroxide the hydrogen that pops off of the acid combined with water in the solution. So what's the chemical formula for hydronium? Do y'all know?
Is it OH or H3O?
H3O, right? So you have an acid and it's gonna have, oops, come over here. Get out of my way, I'm not even using you. Okay, there we go. So you have an acid and it's gonna have something, it was supposed to be a question mark and not a 2. Okay, I'm having a day, something with an H, right? And it's gonna break into whatever this is. It's gonna be a metal ion, right?
Yeah.
And then this H plus. And we're talking about aqueous solutions in particular, so you have these guys floating around. So this guy is gonna combine with this guy, and they're gonna make hydronium, okay? If you leave water alone, there is some dissociating it does by itself. So you get this guy, and then you get this guy. This is what denotes your bases, right? And this is what denotes your acids. And we say that acids are proton donors because this guy is positive, right? And then we say bases are proton acceptors because they want him. Because we want to be friends, right? We want to make water. Yay, water. Water. Gotta have water. So your strong acids are the ones that dissociate completely or nearly completely. So the acids we had today were both strong acids. They're ones that will dissociate completely. They'll lose that H plus in the water, and which means they lose a proton, and that's captured by water to form the hydronium. So what then would a weak acid be? If strong acids dissociate completely or nearly completely, yeah, they don't dissociate quite as completely. So what that means is they don't fully ionize. So while you've got some hydrogen ions, a little positive H's popping off and forming hydroniums with water, you also have some that don't, that stay intact. So, and that just has to do with the chemical structure of the particular acid. So what do bases then? If water generates hydronium, bases generate what? Hydroxide, and that's that OH, right? Anything that ends in OH or has hydroxide in the name, you can pretty much guarantee you're dealing with a base, right? What was the base we used today?
Sodium hydroxide.
And the formula was what?
NaOH.
NaOH.
No, we can't.
So just like, not now. It almost looks like Noah, but not. Yeah. It's the dyslexic Noah. So,
No, this
Noah's Arch.
yeah, there you go.
Noah's Arch.
Noah's Arch.
That was ours.
So if a strong acid is one that dissociates completely, then a strong base is also going to be one that dissociates completely or nearly completely in an aqueous solution. So when they ionize into the water, they're going to yield the hydroxide ions, which is the OH negative. And then your weak bases are the ones that are going to be like your weak acids. They're not going to dissociate as well. Now you've got weak acids and weak bases everywhere, right? Remember when we did the little, is it acid or a base? And we guessed things like milk and stuff that's all around you all the time. But it's the ones that are the strong ones that are really good to use in lab because it's really clear what they're doing, right?
So what is sodium hydroxide on the pH scale?
What is it on the pH scale? It's really, really high. It is, I want to say it's closer to 14.
Yeah.
Let me see. I have it in a graphic somewhere, but it's it's 13. Yep, there you go. So pretty darn high. And the HCl pH, that one's very high. That one's very low. That's 3.01 for HCl, and then H2SO4, which we used, is 2.75. Okay.
And
So-
all the chemicals they use in lab were all just diluted by water, right?
Very diluted, yeah. So the ones that we had, the 1 molar sulfuric and the 1 molar HCl, I bought prepped. They were already done. But the NaOH that we used, they wanted 0.3 molar. And so I had to create the 0.3 molar. And, you know, you have to put the certain quantity of water and the certain quantity of the NaOH together to get the 0.3. And remember I was saying there's awesome calculators now, whereas when I was doing it, it was like bring out the TI and start your thing. But there's one here called Lab Hacks, which is super. And I've used Lab Hacks before, but right here in the dilution calculator, I told it that I wanted to make, that I had, the stock concentration I had was 1 molar, and I wanted to make 250 mils of 0.3. And it says to me, okay, so you're gonna put 75 mils of your reagent, which is gonna be my NaOH, and then you're gonna put 175 mils of your solvent, which in my case was water, because we were doing an aqueous solution, and you're gonna mix them up and there's your 0.3 molar. So, which you can figure out if you're doing about a third, this makes sense, right, for 250. But that's, these are great, man. I wish I'd have had that on my phone back in the 90s. That would have been nice. So the Arrhenius theory. You guys probably saw a little bit about Arrhenius. We talked about Arrhenius acids and Arrhenius bases and all of this. So Arrhenius was a Swedish chemist, and I'm going to try it. It's Svante Arrhenius. Svante, S-V-A-N-T-E. Yeah, Svante. And he was the one who proposed the first definition of acids and bases. And he, it was substances A and B, and he called them acids and bases. Go figure.
Wow.
Right? Yeah.
Wow.
I could not find anything on him in the book, and I know one of the homework questions had to do with it.
Yeah, a little bit. Yeah.
So that one I had to look up more about.
Good.
But
That's good. No, that's good. So what he said is acids are substances that dissociate in water and produce H plus ions, and bases are substances that dissociate in water and produce OH negative ions. That was his definition, which is a good definition. But then we had Bronsted and Lowry come along and give a more specific. So instead of just saying they dissociate and produce, anybody want to like throw something at him?
Cool.
What are we gonna throw at him?
oh no, don't remember.
Oh, okay.
He's away. There we go.
I like watching him.
I'm gonna get a water pistol, I think, and I'm gonna start shooting you guys with it. That's what I'm gonna do. It's like, I thought you liked me.
He does. He got 5 hours of sleep last night.
I'm tired.
Why?
I couldn't
Yeah,
sleep.
7
Oh
hours.
my gosh, take a melatonin.
I did.
So,
Three, yeah.
Bronsted.
20 grams.
So Bronsted and Lowry decided that they were going to describe acids as donating what? Acids donate, yes, in the form of typically your H plus, right? And so they defined their acids as proton donors. And then what did they say about bases? They accept what?
Proton.
They accept the protons. So instead of saying the bases produce hydroxide, they decided to phrase it as the bases accept the protons. And they can accept it from another molecule. They're going to be proton acceptor.
Acids the donator.
Acids donate because they give off that H plus, and then bases accept because they have an OH that's now all by itself and it's negative, and it really would love that little positive hydrogen to join it, and they just make water and now they're all happy. All right, so then what are conjugate acids and bases?
Conjugate acid is an acid that forms when the base is more than the protons.
Okay, what do you have?
Basically that.
Basically that. Okay, so conjugate acids, Bronsted Lowry, this is them again with all of they're the definition dudes, I swear. So they said it's a species formed after the base accepts the proton. Okay, so when the base takes the proton away, you have the conjugate acid left behind.
So it's an acid minus H plus.
Right. So with our HCl, what would have been the conjugate acid?
Chlorine.
There you go. That's right. And then what would have been the conjugate for the NaOH with the HCl?
Salt. No.
With the NaOH. Yes, the sodium. Okay, there.
Conjugate salt.
So these are what we call conjugate pairs, right? So if we look at in lab, you guys are such goobers. So in lab today, we
What did I do?
not you.
Awesome. What about the goobers?
Well, you know this. So we had this HCl, right? And then we had NaOH. So our pairs that we're looking at here are these parts that are left behind. When this goes away, and this goes away. Right? So they form, the conjugate pairs here, or what are they gonna form every time? A salt, right? And in this case, what was the salt? What? Oh, the salt was what? NaCl. So we just formed table salt today.
Wow.
Yeah,
Good job, us.
good job.
Table salt and water.
Yep.
So do we have to?
What? I missed it.
So if we got rid of the indicator solution, we could boil it and we end up with,
Salt.
yeah.
Yeah, absolutely.
Yeah.
And because we put the phenolphthalein in there, we know it was neutral because it changes from clear to pink at neutral
Ah.
or basic. So at that point, now we're gonna learn next week, there's this whole transition phase where like an indicator will have a phase, and it's really hard to see in that tiny little test tube. But if you had a bigger volume, you could be more specific and you would see the shade change.
Yeah.
In that tiny test tube, it tended to go
I
like
think I saw a shade change. What if ours was more red?
yeah, and I looked at some of them. Some of them were very light pink, and those are the ones that are just tipping, which is right on the line of
Yeah,
going
neutral.
from acidic to basic. So there's always going to be a range, and sometimes it's a range of color that's more obvious. Like when we did Rummethil blue back in the fall, we had those little flasks, and you guys blew into them. Do you remember that? And you blew into the water with the indicator and it created an acid which changed it from, was it blue to yellow? But as it goes, you can see the color shift more from blue to green to yellow. Whereas this one in particular just goes like lighter pink to brighter pink, right? So these are conjugate pairs. They're gonna form your salt, and then you're always gonna have, this is your water, right? If you get a neutralization, you're gonna get water and salt, which is cool because you know what you're looking for every time. So what do you call something that can act as both an acid and a base depending on the situation? There's a word for those.
What?
Yeah.
Oh,
Amphoteric. Okay, so amphoteric, these are the ones that can be both acid and base. Water can be amphoteric. So it's a compound, especially a metal or a hydroxide.
Is pure water 7 on the pH scale?
Pure water is 7 on the pH scale, but
So distilled water?
yes, but water will dissociate on its own. It will self-ionize. So when that happens, it can shift things. Y'all are right over there. So it is able to react as both an acid or a base. So here's our Bronsted-Lowry guys again. Johann Bronsted and Thomas Lowry. They revised Arrhenius's acid-base theory to include this behavior they defined acids and bases. Acid is a hydrogen-containing species that donates a proton. A base is any species that accepts a proton. So you'll notice they're leaving out the hydroxide in their definition. They're saying it accepts the proton, it's a base. And so here it says in the above example, what is the Bronsted acid and what is the Bronsted base?
The acid is hydrochloric acid.
Mhm.
The base is water.
The base is water, right? So because when you combine them together in our aqueous solution, like we combine them here, you are going to have some of the water dissociate. And when it dissociates, you're going to get hydronium, which is going to be it's a basic substance, and you're going to end up leaving that chlorine floating around by himself.
What are we talking about?
We were talking about Arrhenius and Bronsted and Lowry.
Oh.
So more on Bronsted and Lowry. Dude, are you okay? So
More and more.
in reality, the reaction of hydrochloric acid with water is an equilibrium and occurs in both directions, right? So you've got it shifting back and forth. Although in this case, the equilibrium lies far to the right. So for the reverse reaction, chlorine, which is a negative chlorine ion, behaves as a Bronsted base, and then the hydronium behaves as the acid. And then what is the deal? For real. And then the chlorine is called the conjugate base of HCl. So Bronsted acids and bases always exist in conjugate acid-base pairs. Their formulas differ by only one proton, right? Okay. So here are some conjugate pairs. So this is what we just looked at up here on the board, and it's up there on the screen now too, you can see. So you have your HCl and you have your NH3,
Yeah.
and you can see your conjugate pairs there. And then you can also see here you have a conjugate pair HCO3 negative, and then your CO3 negative, because it's talking about getting rid of the hydrogen, right? Right. All right, so acidity, basicity, and pH. So here is a graphic for you, if you want to see, about water dissociating. It's what I wrote up there, but it's done with little bubbles instead. I think you're supposed to color this in. It's cute. So you have your little Mickey Mouse water molecule, right? They always look like little Mickey Mouses.
Yep.
And they will dissociate all on their own. And you're going to get this hydroxide and then a hydrogen. And then this other water will be bobbing along, minding his own business, and that random hydrogen will bump into him, and then boom, now you have hydronium. So this is how you get,
Mickey Mouse with a goatee.
this is where you get the more basic behavior. Mickey Mouse with a goatee. Oh yeah, it does kind of look like that. That's funny. That's funny. So here are some key points that I snatched for you. This is off a really good chemistry website. So water can undergo, you good, Cole? Water can undergo autoionization, and that's when you get your hydronium and hydroxide ions. And equilibrium constant. So we talked a little about this, but this is a number it's used frequently. The KW, or the equilibrium constant of water, is 10 to the negative 14 at 25 degrees Celsius. This is something like the number pi. You just use it. It's just a known number, and you just plug it in. The autoionization constant for water.
Okay.
That's the number we use. We just plug it in.
It's how fast it ionizes, or
It's
A number.
thanks.
it's not fast. It's how.
Well,
Yeah, that's a way to describe it.
it
It's kind of weird.
completely
Yeah,
work?
I mean, it's at 25. So obviously, if you change the conditions, it can auto-ionize. Its efficiency, I guess, is a better word for it. How?
when would you need to use that number?
Okay, so there will be some. There actually is a problem. Is it this week or next week that you use the constant for? So there will be problems presented to you when you need to know the autoionization constant.
Put it in like a word problem.
Yeah, that's where it'll be, like in a word problem. I think there's one in here.
Type of word problem.
Yeah, I think we're gonna come to it in a minute. I think it's either in here or it's next week, but it was obvious that you needed to know it because it was like how many hydronium would be produced using so many moles of, can't remember how it was phrased exactly. So it gives you right here, neutral, acidic, and basic. So in your neutral solution, you're going to have equal amounts of hydronium and hydroxide. In your acidic solution, you're going to have more hydronium than hydroxide. And in your basic solution, you're going to have more hydroxide than hydronium, right? Because the hydronium is what's denoting you have the acid because the little hydrogen is floating around by itself. Like when we looked at lab today, the more hydrogens we had, right? The more hydrogens we had involved, that means we have more opportunity to make hydronium, which is going to make something more acidic, and it's going to need more. And if you look at the pH of those particular acids, like we just did a minute ago, that can kind of help you relate today's data too. So right here, for aqueous solutions at 25 degrees Celsius, this is the relationship again. It's KW right there. And if you look, Michael, it says H3O plus and then OH negative. There's the 10 to the negative 14 again. So it's the pH plus POH. So remember, pH is how many hydrogens, so that's your acid. And POH is base. And remember that the pH scale and the POH scale are like mirror image. So one is telling how basic something is, and one is telling how acidic something is. We typically use pH, but if you use POH, you're denoting, it's like you're comparing it to a base standard as opposed to comparing it to an acid standard. So
something really acidic on the POH scale would be like 14.
yes,
Yeah.
exactly.
Wow.
So here's your Y is pure water 7. All right. So this is just a little, I grabbed this because it gave some interesting numbers, but in a giant number of water molecules, 500 million water molecules will auto-ionize. So here you have your H2 and your H2, and they're going to yield your hydronium and your hydroxide, right?
Yeah.
So this yields a hydronium ion concentration of 1 times 10 to the negative 7 of hydronium. Because you're going to have 1 times 10 to the negative 7 of hydroxide, right? Because it's 1 times 10 to the negative 14 for the constant. Does that make sense?
Yeah.
There you go. All right. So what you end up using is this logarithm. Now we haven't done that, and a lot of people haven't done that. And
I'm doing that currently.
yeah, so I did put a little blurb in here about log and logarithm. It's coming in one of these next few slides, but
I study log. That will log into my brain.
we'll get to the log in a minute.
I was thinking of a big old trunk.
Okay. So amphoteric again.
Logarithm.
Long.
Substances can act as either proton donors, acids, proton acceptors, bases. So here we have acid and a base, and they've termed it here C, because that's your conjugate pair, plus your acid, and then C plus your base. That's not a great graphic. There we go. That's the one I was looking for. It came out of order. So here's your acid, here's your base, and then it's gonna in this case produce for you some of these hydroniums, and it back and forth, back and forth. I don't like this slide. Let me go to the next slide.
CACD.
Yeah, that one wasn't.
What?
I think one of these got copied backwards, so don't look at that one. Look at this one. So looking at your next section, B, the meaning of pH. All right. So we have pH and acidity, right? So what's neutral?
7.
In your notes, yep, exhibiting neither acid or alkaline qualities, and it's going to be 7. And then pH. Okay, so what's pH? It's a measure of hydrogen ion concentration. pOH is a measure of hydroxide ion concentration, right? So pH is your measure of hydrogen ion concentration, and it's a measure of acidity or alkalinity of a solution. Technically, it's a measure of acidity, because if we're doing alkalinity, we would be doing pOH. But it ranges from 0 to 14. And you calculate it from the hydronium, which can be done. But I was going to go do this for you, this little bit for you first, because this is interesting history. So what does pH mean? So I was telling the other class that one of my standout memories from junior high was asking my pre-algebra student teacher, whose name was Ms. Prisborowski, what pi meant. And she told me that it was 3.14. And I said, I know what it is, but what is it? And all she could tell me what it was 3.14 and gave me other couple decimals. And I was like, but you can't just throw a number out and go, oh, this magically works. Like, what is it? How did you get that number? And
Notes.
she ended up crying, turning into like a slobbering mess. And I felt like dirt. I felt awful because I wasn't trying to, I did not mean to upset her. I just wanted an answer and I wasn't getting it. So, and I was telling them, because they were all like, she cried. That's what your younger guys were like, she cried. And I said, well, here's the other thing you have to understand. There were 2 boys in my class named Mike and Edwin, and their entire goal was to just poke her until she lost her mind. And they would be like, yo, Miss Priz. And then they would ask poor Miss Prisborowski, and they asked her to do something else. And she was like, I mean, she was so fragile at that point. And I've teased Mike since then because he's now a minister. And I'm like, do you remember that student teacher you tortured? Yeah, her, back when you weren't a minister and you were a little troublemaker. But this is the same kind of question. Like, where do you get this pH from? What's the P? So there's a lot of, there's been a lot of, not so much controversy, but confusion about what the P means. So the exact meaning of the P in pH is disputed. So as Sorensen did not explain why he used it, this is SPL Sorensen in the bottom corner there. He invented the pH scale. He didn't explain why he used it. He described a way of measuring it using potential differences. So there's a P in the word potential, right? And it represents a negative power of 10. So there's another P in the concentration of hydrogen ions. It's a negative power of 10. So think of it again about your water constant that we just said. 10 to the negative 14. Okay, so if we're dealing with powers of 10, all right, now we had a 14, 7 is neutral. These are all in the exponent, right? So it was a negative power of 10 in concentration of hydrogen ions. So he says here that all the words for these start with P in French, German, and Danish. And those are all languages that Sorensen published and spoke in Carlsberg Laboratory, where he worked, was French speaking. Yeah, well, was a French speaking facility. So he was very fluent in French, but German was the dominant language for scientific publication. So obviously he was very fluent in German, and he himself was Danish. So he could speak all 3. So people have thought, well, maybe that's where the P came from, one of those words. But he also used Q sometimes. And it shows up in his papers just about as frequently as the P. So the P could stand for the French word puissance, or the German word potens, or the Danish word potence, and they all mean power. Or it could mean potential. We don't know, right? He might also have just labeled the solution P, because sometimes people use P and Q in a laboratory to denote two solutions they're working with. Like these two have a relationship, but they're not the same solution because P and Q are a mirror image of each other as a symbol. So they just are used like a set. So maybe he just randomly picked it and he just, it says there's little to support the suggestion that pH stands for the Latin terms pondus hydrogen, which is quantity of hydrogen. Some people say that that's what it stands for. There's not a lot to support that. Or potentia hydrogeni, which is the power of hydrogen. So currently in chemistry, the P actually stands for what you would say if you were speaking it as a mathematical formula, which is decimal coalgorithm of. So we leave it as decimal coalgorithm of, right? And
How do you spell
right. And it's the term like in pKa is used for acid dissociation, and POH is the equivalent of hydroxide ion. So it's technically decimal coalgorithm of, but I know he may seriously have just put a P down for the sample he was using at the time, and then that
My
became.
favorite letter is P.
Yeah, I mean, it is one of his middle initials. Who knows? So if we calculate pH from hydroxide, this is where the log comes in. So pH is negative log hydroxide. So what is this? All right, what's the log? So a logarithm is the power to which a number must be raised in order to get some other number. Well, that's not very helpful, right? So for example, the base 10 logarithm of 100 is 2, because 10 raised to the power of 2 is 100.
Oh.
So think of it that way. 10, if you're using base 10, and we're going to use base 10. So if you're using base 10 to the power of 2, you're going to get 100. If you use your calculator, very often it's going to be an E or an EE. There's lots of different ways it can show up. So log of 100 is 2 because 10 squared is 100. So this is an example of base 10 logarithm. We call it base 10 because 10 is the number that is raised to a power. The base unit is the number being raised to the power. There are logarithms using different base units. If you wanted, you could use a 2 base unit. We're not gonna. But for instance, the base 2 logarithm of 8 is 3 because 2 raised to the power of 3 is 8. But we're not gonna do log 2. If you see log, and it'll tell you in a second here in my notes, but if you see log by itself, the assumption is 10. In general, you write log followed by the base number as a subscript. The most common logarithms are base 10 and are natural logarithms, they call them, have special notations. Base 10 logarithm is written just like this, log. So if you see log, it's 10. If you see log with any subscript, it's something else. But log by itself is 10. So here's how you do it. So calculating pH from this hydronium here. So what's the pH of a solution with the following hydronium ion concentration? So if this is your hydronium ion concentration, then it's actually way easier than you'd think it would be. So this should play here. There we go. So you're going to do 2.4 EE, because that's your exponent, negative 10 equals. So I'll do it again. So you go 2, if it'll go play, 2.4 EE, which gets you, that's your log button, well, 10, right? Exponent 10. 10 gives you this number. So right here is what you did. pH log 10. So you do pH equals log. There is your concentration, 2.4 times 10 to the negative 10. So first, you enter this into your calculator. You use the key EE or EXP, depending on what your calculator says, for the exponent. So you hit the equals key first. So you do, first you enter this, 2.4 EE, negative 10, then you hit equals. Then you hit log and take the opposite sign. So do you see the log button? Take the opposite sign. And in this case, we get 9.62, not negative 9.62. So watch that again. So first you enter the number 2.4 times 10 to the negative 10, and you hit EE to get that, right? And then you hit equals, and you get boom. Then you hit the log key, and then you get that, and you take the opposite sign. So your calculator actually says log 10, right? It's right here. That's what you need to
How
get.
did you get 2.0.2.4 out of H3O?
So it says, what is the
Is it
pH
H3O
concentration
or
of a solution with the following concentration? So you're given the concentration as 2.4 times 10 to the negative moles. And then you put it into the calculator as such. And then you take the log.
Yeah.
Because what we're looking at is negative log. So you have to remember it's the negative log. So that's why we do the opposite sign, right?
Yeah.
So here's a graphic for you with your H plus and your OH negative. So your H plus is your concentration of ions, and that's your pH. That's this right here, right? The more hydrogen ions you have down here, the more acidic it is. And here's your hydrochloric acid way down at the bottom, gastric juices, vinegar. I love the word gastric juices. And then your POH is over here. That's your concentration of hydroxide. And this little graph here, this has got all kinds of fun math in it, but here's how you go again from concentration of ion to POH, or concentration of ion to pH, which is what we just did just a second ago with the calculator screen. So this is how you go from pH to POH. This is how you go from POH to pH. See right here, hydrogen and hydroxide, POH and pH, how you go from pH to hydrogen ion concentration and back again, or the other way around. And I can send this out to you guys if you like it. Nice to have. Yes.
Please do.
Nice to have. Yeah. Oh yeah, sure.
What?
One more on that.
The one with the calculator.
Go with the calculator. Yep. That's this one. Whoops. Go back. Go back. Go back. Go back. There it is.
Alright, is it that many moles in, it's the concentration of H2O in what?
It's the concentration of hydronium.
Oh, okay.
So you want to know the pH of the solution with a certain hydronium ion concentration.
So
And the
then-
concentration's known. Like say I gave you, okay, for example, we use that 0.1 molar HCl today.
Yeah.
If you wanted to know the pH, then this is that we would use that molarity here.
0.1.
Well, actually we wouldn't use, yeah, we would. Mhm. And then you could work that out and it would give you your answer.
Yeah.
Sort of clear as mud.
So it's the concentration of the thing you want the pH of? Or
Yeah,
the
so this
concent-
was an example of how to get, so you want to know the pH, you're given the hydronium.
Okay.
You could be
You're
given
finding-
hydroxide as well.
On this slide, you found the pH of H2O or the pH of,
In this side, what we found is the pH of the solution
okay,
that has this molarity.
but we don't even know if it's
We don't know what it is. We don't know what solution it is. We just know it's molarity.
the molarity of H3O.
Yep.
Okay.
There you go. So measuring pH and indicators. All right, so we had an indicator today. What's an indicator? Yeah, what you got?
A compound that can reversibly change color depending on the pH of the solution or other chemical changes.
Right. So any substance that gives a visible sign, usually it's color, for the presence or absence of a threshold concentration of a chemical
You said
species.
usually it's color. What are other ones?
I
Smell.
can't even think of any others, but I'm sure there are. Just all the ones in my mind
What do you
are
think?
color, but
Digital?
what?
No, never mind.
I'm sure there are. I just can't think of what it is.
Digital?
Well, there are, I mean, we do have, I do have pH meters, but that's not an indicator. That measures, but doesn't indicate a change. So it's a little different. I can't off the top of my head think of any that aren't colored. So pH meters, what's listed here. So that's an instrument that's going to measure the hydrogen ion activity in water-based solutions. So indicates the acidity or alkalinity expressed as pH. So we have a pH meter, and I'm pretty sure there's also a probe that goes with the TIs for the CBL units that can do that as well. So the pH meter measures the difference in electrical potential between a pH electrode and a reference electrode. So actually our colorimeters, they had a pH system attached to them too. And something else we've used recently had a pH, I can't remember what, but something else we used recently also had the ability to test for pH. So the pH meter is sometimes referred to as potentiometric pH meter. Nobody says that. I don't know why I said it. Okay, homework stuff.
Oh, uh-oh.
So could a Bronsted-Lowry acid not be an Arrhenius acid?
No.
Does anybody have an answer?
Yes.
I do have an answer.
You can grab it. You can grab it if you want. Yeah, yeah.
Can you grab mine
No.
too?
Oh, grab Abby's. Thanks.
I know mine's probably wrong.
Mine's
probably
wrong. Mine is,
It's okay.
yes.
I'm calling in
Water.
math questions, which is probably the first time I've ever said that in my
Yes.
life. But you know.
Just Abby's.
Yep, yep. There you go.
Yeah.
So what did you
So
say?
I said yes because Bronsted-Lowry doesn't have to be in an aqueous solution while Arrhenius does.
Okay.
And water's around Lowry, but not Arrhenius.
Okay. Abby, you have anything different or? He's like, no. So,
Because when I looked up
Yes.
Arrhenius, it was had to be in water.
okay. Yeah, so for instance, in the gaseous phase, hydrochloric acid donates a proton to NH3 to form NH4Cl. So the reaction does not involve the production of hydronium ions. So hydrochloric acid is not acting as an Arrhenius acid in that case. There are cases. I think the book just wanted you to think outside the box for a minute. It's pretty much your standard that you're going to be thinking of Bronsted-Lowry acids and bases most of the time anyway, because that's pretty much how we function these days. So can a pH be negative? What'd you get, Cole?
So yes, pH can be negative and it can also go above 14. And I think that I answered this correctly. And I said, given the nature of pH scale, some acids will not appear to be negative in the equation form, though it can be hard to determine if this is true.
Anybody have anything different?
I wrote it can show up on a scale as negative, but you can't have a negative concentration of something.
Okay, that makes sense. Yeah. So pH is whatever the hydronium concentration. pH is negative, sorry, whenever the hydronium concentration exceeds 1 molar. So yeah, it could be, but we won't be using them because
That
that's
would be great.
scary. Mhm, yeah.
There's like a negative, there's a very, very, very high very negative acid that has to be carried in special Kevlar lined
Oh, I'm sure.
containers.
Terrifying.
Otherwise it would melt through the container.
Yeah, we're not using that here.
Can I touch it?
Although I'll say,
There's
one
It
of
would
the-
melt you.
so the company that I order a lot of our lab supplies from is Carolina Biological, and they're really good. And they were great because they wouldn't, it's like certain things they wouldn't let me just order. I had to talk to somebody because they're like, oh, you can't, we don't ship this, it's dangerous. And if you have a school code, you just put it in. But of course, we don't have a school code. So I talked to
You should
this
make
dude
one.
there. Well, I talked to this dude there, and he was like, oh, yeah, because I have in my email signature, it has the website and everything. He's like, I already looked. Y'all are legit. He actually said, you have a very well-stocked lab. I was like, I sure do at this point. So he said, from now on, you just call and you can get anything you want. So when they shipped me, one of the last things I needed, it was like a liter of concentrated hydrochloric acid. So it came in its glass bottle with its lid that was taped on with electrical tape. Inside, now they pack things in bags with this like absorbent, it's kind of like have you ever seen corn cob bedding for like small rodent animal pets? It's like a mix of that and some kind of fiber. I don't know what it is, some kind of kitty litter looking stuff. They pack a lot of chemicals in bags inside of that. This came inside of that, inside of what appeared to be a metal paint can inside of the box. So, I mean, they're really careful about sending stuff safely.
I wonder if they have anything in their inventory that requires a whole convoy of vehicles.
I don't know. They have all kinds of things. They have live specimens and they have, I mean, we'll be using them a lot next year for bio too. I'm excited.
I think it
But,
was too much.
The fact that he was so cool to me and he was like, yeah.
Sounds insane.
He said that they really like homeschoolers and they're trying to figure out how to better work with them. And I'm like, I'm your girl. So So observable properties of acids. So this is observable. It's in front of you. What are the observable properties?
Of
Acids. Mhm.
Oh,
oh yeah, they conduct electricity, they react with metals, and they generate hydronium ions.
Okay, those are good.
Yeah.
Anybody have any different ones?
no.
No?
I got basic, no.
So they're also sour.
Oh.
They burn your nose.
You know, I've never really tried them, actually.
Really? You've never had
No,
vinegar?
I've never drank it.
Never had
No,
vinegar?
never
No?
done
You
None of
have
that?
to drink.
Not a pleasant experience.
It is observable if you don't want.
It is observable. You might die observing it, but it's observable.
Hijack.
So they're sour, they burn your nose,
Bigger problem.
they're sticky, and they react with metals and indicators, and yes, the whole hydronium and they'll conduct electricity. If you open up one of the bottles of the concentrated hydrochloric, for example, if you open it up, you can see it vaporize and you can smell it from 3 feet away. It's really like up, and better have your eyes covered because it burns your eyes and your nose. It's rough. So bases, what are the observable? Oh, right over there. Yes, what you got, Cole?
They can come in the solid form, they generate hydroxide atoms, and they conduct electricity when dissolved in water.
Good. And they're slippery. They're also bitter. We say bases are bitter, and they usually don't smell.
The base.
hmm And they react with oils and fats.
Those are
It's also, you know, it's empty.
just some of the basic
Is oxygen a base?
qualities of them.
Good question.
Yeah.
So here was the math problem. Calculate the hydroxide ion concentration in an aqueous solution that has a concentration of hydronium ion equal to 1.55 times 10 to the negative 2. So did you use an app or did you do it by hand?
I used website.
Use a website, okay? Use a website. So you can totally use the apps for this. This is why they're good.
It is sort of by hand.
Yeah, so if you were doing it by hand, what you'd get is this. Here's where you use KW. It's asked where you use KW. Here's where you use it. So because it's asking for the hydroxide ion concentration in an aqueous solution that has a concentration of hydronium equal to 1.55 times 10 to the negative 2. So you're going to take that KW, which is your constant for water, and that's 1.00 times 10 to the negative 14. And you're going to remember that the OH and the hydroxide are going to be inversely proportional. All right. So what you get is, and it's up here, you got the OH negative and so you get the hydroxide and the hydronium, and they're going to equal that standard for water. And then if you plug that number in, then you end up here, and you end up here. Is that what you guys got, or something very close?
6.309 and
Yeah.
negative
Okay.
12.
Oh, negative 6.3090. 6.309?
Yeah, 6.309.
Point-
Pretty sure that's what I got though.
Okay. Oh, that might be right, actually. I think I typed it wrong because look, you got a 14 and a 2, so it has to be
You've got a
Maybe
brownie
the
point.
13. Yeah, that would be 12. I typed it wrong, apparently.
Brownie point.
Not if I found it, it's not.
I got it first.
You already got it.
I found that.
We found that it was wrong because of Cole's answer.
It had to be.
Right, because of Michael's
Yeah,
answer
yeah.
that was given to Cole.
So next, so
Was given to Cole.
So what you guys, the big takeaway points are to remember here that your hydroxide comes from your base and your hydrogens, thereby hydroniums, come from your acids, right? If you can keep that in your brain, that's the big takeaway. And then a lot of the other stuff you can, go out, go away, go away, go away. There we go. So next week, our lesson, you're going to finish up this chapter, right?
I don't know.
Yeah, because you just did 1 and 2.
Then yeah.
So you're going to finish up this chapter and you will move on to, this is 25. Oh, this is the one that I didn't have and I had to write it. So stupid. I don't know why it
okay
didn't show
over
up there.
You're
What's
having a
happening,
good-
buddy?
He's having problems today. We aren't sure why.
Yeah, we're
Your
finishing
problem,
chapter
child.
15.
So you're going to finish 15. And
Yeah.
you'll notice here we're about to finish.
Never mind.
Cool. You'll notice here that we're about to finish third quarter. We are not that far from the end of third quarter. So when third quarter is over, you'll get all of the remaining stuff for your binder, right?
Binder's not full yet.
No.
You have one more quarter left to go. But if you look at your next lesson, there's far less writing done for you. So most of this outline is for you to complete, right?
Y'all
And
are so
then-
discreet about this.
Huh?
I said they're so discreet about this.
You're ridiculous, man. So you're gonna get next week's lab is we're gonna do actual straight up titration with the with our burettes, okay? And it's going to be real titration that involves using the burettes correctly instead of just using them to get used to them like we did today. I highly suggest, especially since you guys are all, everybody that leads a lab group is in this group. If this is no joke, go to WikiHow and look up titration. There is an absolutely excellent step-by-step guide to titration on WikiHow. I randomly checked it because I was like, I wonder if WikiHow, and sure enough, WikiHow has a fabulous step-by-step titration instructions. Now, a lot of the prep work, the cleaning and all will be done for you. So we're actually going to titrate an eggshell.
Whoa, that's
We're gonna find out because the calcium carbonate in an eggshell is a base. And so the overall, the theme of the lab is that you work in the Department of Agriculture and you've got a farmer who has eggs that for 10 years have become increasingly fragile. So he wants to know what's up with that. And it says the farmer believes the problems are linked to a landfill upstream, which is being investigated for illegal dumping of PCBs and other hazardous chemicals. Oh no, so he's messing with his eggshells. So, and it says that you need to determine how much calcium carbonate is in the sample eggshells from the chickens that were not exposed to the PCBs, and the farmer's eggshells, we know how much they have, and we know how much chickens that don't have PCBs. So we're going to find out, and it would be really fun.
Non-PCB chicken.
Yeah, it would be really fun with this lab, and I don't think we will have time, but I would love it if we could get just one day for fun. If we ever have time, it would be great to get some eggshells from some local chickens that people have. And some like, yeah, get like some local chicken eggs, get like some Eggland's Best, and then get like some Walmart eggs
Can we
and
make,
compare them.
like, can we get a ton of eggs and like make eggs for everybody and then make the egg shell?
Bro, I make the best cheesy scrambled eggs.
Ooh, I love cheesy scrambled
I
eggs.
just ate, but now I'm hungry again.
No.
So there's prep work for the lab.
You get hit in the face by an egg at like 20 miles an hour.
Yeah.
I don't know.
So there is prep work for the lab that involves drying the eggshells, and I've read over it. So I want to make sure you guys know this before you come next week. I've read over it, and it wants you to like peel the membranes out of the eggs and put the eggs in the drying oven, and then leave them there for 15 minutes, and then move them to a dehydrator. This is all time I worry we won't have. So I will probably, when you get here, your eggs will probably already be in the dehydrator, because I will probably have done the drying and all that ahead of time, just because, you know. But you will be using not only the burettes next week, but also mortar and pestle, which is so fun.
So fun.
I do it. Wait, Jack, you want to do something?
Why me? What?
Mortar, you want to use the mortar and pestle
What?
next week?
Sure, Capitan.
If you don't like to go
Y'all
out,
are hilarious.
Did you just say Capitan?
He did.
yes, he did.
He did.
Yeah.
I do want to show you real quick, kind of an overall where we're headed, because we are getting to the point where we are nearing the end, folks. Really, we are. And I'm so happy because I really just can't wait for biology. One thing to note, it is now the 23rd, which means by the time we meet, listen, by the time we meet again, it will be March, right? Because today is the 23rd.
Yeah.
I am saving a seat for everybody in this co-op for next year until March 1st. March 1st hits and I'm opening it to everybody. So if you want, if you want your seat and you want to be sure you have your seat,
I don't care if I
go ahead and have make sure your mom or whatever contacts me. There's supposed to be a deposit, but I mean, if somebody wants their seat and they don't have the deposit, I will waive the deposit and get the seats, you know, because it's a real pain for somebody to come back later and go, oh no, we decided, and then I don't have a seat, but it's somebody I've had for years. I definitely am going to squeeze them in. So then it gets a little wacky.
I always
So-
have a small corner.
You always have the small corner. You like it.
I do like it.
That's why I
yes.
put you there.
I'm just saying I have a small corner.
There you
That
go.
would be
If
okay
I-
how
if
A
I
now.
pay
So
extra
let's take a
deposit,
quick-
Can I stop Ethan from coming to class?
Oh, man.
Well,
You're nice.
Unfortunately, you
would,
can't.
would be.
So I just want you to take a quick look at where we're going. So next week is March 2nd. All right. And that's going to be our lesson 25.
Yay.
And then we have our lesson 26 and our lesson 27. And that's it. That begins Q4. At that point, we're gonna be in Q4. Now- Listen, keep in mind that the majority of things you're going to get graded on that are not the big final thing are going to take place in Q3. In Q4, there's not as much to grade because the last couple weeks, there's a lot of reviewing and prepping and project planning. So keep that in mind when you're taking your next test or two. Also, we've got then lesson 28, and then it's a spring break. Our spring break is 2 weeks long. It's 2 weeks long because Forsyth County scheduled their spring break on one side or the other of Holy Week. I don't remember, but I have to take Holy Week off. I always do. So Holy Week and then whatever week it is
We get 2
before
weeks
after.
off in a row?
2 in a row. So not here on the 30th of March, not here on the 6th of April. You come back at lesson 29. And by then we are moving from, so we wrap up before spring break. Shh, guys, we wrap up before spring break, our electrochemistry, oxidation reduction, all that kind of stuff. And when we come back from spring break, it's nuclear and organic. And we will go from nuclear is very short. It's just like little bit. It's less than what? 29, 30, 31. We're already in by lesson 30. We're out of nuclear. It's a quick little dip. And we're into carbon and organic, which leads us into bio.
Which is okay. Yeah. I like
And it's going to be super cool because our last couple of labs, for example, we have a couple more titrations coming up. So we have, where am I? Okay. So next week we have where is it? There it is. Next week, we're doing the acid-base titration of an eggshell. Then we're doing reaction rate lab, and then we're doing electrolysis of water, which means we are taking water and splitting it into its 2 gases.
Which are both flammable.
Yeah. And there is a part of the lab that requires you to take a match and it goes, pop. Yeah, it's going to be fun. Mhm. And then after that, after the electrolysis of water, we're going to do one more titration. Shh. We're going to do one more titration. It's a redox, so it's oxidation reduction titration. Then we have a mystery lab, which goes with our nuclear power lesson.
Yeah.
Yes,
I have a question. I forgot. Do the teams change every quarter?
every quarter.
Yes.
Okay.
Yep.
Miss Patty,
I couldn't remember.
And then
We're
later,
just keep the same.
look at that. Well, hang
I'm
on.
also down.
Lesson 30 is going to be a fun lab. We are going to make toy bouncy balls because we're going to make polymers, and that will be fun.
You're just-
And then, no, it starts to get really fun to the end. And then lesson 31, which is our last, one of our last labs. Well, we're doing, it's a game, it's a DNA RNA game. Our absolute last lab is lesson 32, and we will be isolating the DNA of an onion, which means we'll be pulling it out and looking at the actual DNA. Super cool,
Oing, oing.
right? And then it's review games, and then it's, it's project. So project and finals.
Do we
So
have-
we're
oh,
closing in
okay.
on the end. Yep.
I was hoping that our project would just be our final.
I thought so too. I was like, oh yes. Grab that front.
So that project is looming. Don't forget about it. And I do have in here that we can always do the pool party, but that's totally dependent upon whatever COVID restrictions. Because last year they didn't open the pool until forever. Yes.
We'll probably find
What
out.
was the-
I don't know. You're talking about lab teams. Yeah.
Will there be a Jeopardy review game?
Yes, if that's what y'all prefer.
Yes, there is.
Also,
Those are
can
my
you-
I
least
also saw there was
favorite.
gonna be pizza.
Yes, there will be.
Pizza?
Yes. It says so in your notes and in your syllabus and all, but on the final day, you're gonna come in at 10 o'clock. You're gonna do an in-person final. Yeah, you come in at 10. You do your in-person final, right? And then you sit quietly till everybody's done by 11:15. So it's only an hour and 15.
Pizza.
Yeah, we're gonna watch our presentations. So 11:15, 11:30, we're gonna set up, we're gonna have our pizza party and project presentation. So the pizza party eating will be the audience to the projects, yes.
Are we gonna have like some kind of like study guide that can print out and do at home?
Yeah, sure. If that's, yeah.
Yeah, please.
Mhm.
That really helped me last time.
Yeah, yeah.
I had to study.
They threw a lot together. These guys over here did. And,
Just do it again, guys.
yes, absolutely.
Yeah.
Hmm. Well, that's one of the cool things about the forum is that you guys can work in there too, and you can, like, okay, so for example, Chicky next door, who's in 10th grade at public, she, for some AP class she was taking, she told me, because remember when they shut down everything in March, right?
Yeah.
And she's like, we got a review packet and it's like 120 pages and that's all we have to do. We just have to finish the review packet. And I said, so let me guess, you and your friends, Daisy, I said, you and your friends decided who was doing page 1 through 5, who was doing 5 through 10. She's like, yeah, and then we just copied. I said, because that's what they did. They didn't have the exams because they weren't counting them for anything. So basically all they learned was whatever pages, or all they really practiced was whatever pages they designated, and then they just copied.
Yeah.
But you can definitely, for something where there is an exam coming, that's a beneficial thing because you can each go through and research whatever parts, fill them in, and then share all of that with everybody. Yes.
Can we work together for the final exam? I don't think that's right.
Not on the exam,
I'm
but for the
saying.
studying, yes, yeah.
I was like, oh.
Yeah. Not on the exam, but yeah.
Yo, what's your short answer for 18?
Yo,
Yeah, what up?
So funny, bro.
So yeah, it's coming faster than you think. It truly is. And next year, we're starting in August like always. And I've got already, yeah, we always start in August. And I've got in this class already 1, 2, 3, 4, 5 maybe that are already signed up. That are already,
For what? For biology?
yes,
Cool,
from this class. Yeah, I guess I'll teach Cole again. God. So yes.
It's such a bothersome task.
Right.
Oh,
So a lot of
I
you,
was gonna
and
be a
it's,
lab
and there's only one of them
technician.
that's new, and it's your sibling. So
I
Piper,
believe she's
So
the
that's
lab
like,
rat
that's the country boy thing.
she's this level next year. Yeah, because she's 8th grade and she's gonna come in with you. Yeah,
And you're still gonna be
Dude,
here.
it's like Malay.
My leg.
That's funny. That's what I should know.
it's hilarious. So yes, that will be fun. I mean, some of you did it with me before when we did like half biology with that awful curriculum. This will be awesome. This will be very fun. Huh? What'd you say?
I remember that year very fondly. I don't know what you're talking about.
Yeah,
What year?
it was a fun class, but that curriculum was left so much to be desired.
Remember Aaron?
What thing to remember?
Oh no,
Everything about it.
poor Aaron.
Where?
Everybody loves Aaron. He's in public.
I thought he was. I can remember. Somebody
No,
said
he ate
that.
a flower in front of me once. That was funny.
That's pretty cool.
You hit a flower?
That's the
He
best
just pulled a
one.
flower off a bush and ate it.
No, he was like,
Oh,
hey.
ate it.
Oh.
Yeah, he
Sounds
pulled a
right.
flower, looked me dead in the eye. He's like, "Do you want me to eat this?" I'm like, "No." And he's like, "I'm gonna do it." I'm like, "Don't do it."
That's Aaron. Yeah.
Hey, Aaron.
My favorite from that class was still the time we scared Aniston to monitor her parasympathetic nervous system.
What
That's
happened?
pretty funny.
Remember Aniston? We were ready. We were going to check her pressure. Her pulse and her respiration
yeah.
rate and everything if we excited her nervous system. So we had her sitting so calmly in a chair and she was all relaxed. And then everybody just went, "Rah!" at one time, and I thought she was going to pee herself. It was fabulous. She came up out of the chair like she'd been electrocuted. It was great. But it truly worked. So we all got to do our monitoring there.
What about thwack the bees?
Thwack the bees. That's
Oh,
Henry with
God, I
the
hate
thwacking. The bee
I
thwacking.
forgot about Henry.
Henry's up in Big Canoe.
Yeah, dude.
It's beautiful up there.
Spanish classes to me was more uncomfortable than high school for Thanksgiving.
Yeah.
Remember, you didn't tell us the joke.
Here's the colors.